We're moving on to a new topic now in Math 5, which is that of the matrix of a linear map. So, as we've seen so far, important examples, really important examples of linear maps are the linear maps obtained by left multiplication by a matrix. So if you have an m by n matrix with entries from the field f, then there is a linear map from f to the n to f to the m, given by Ta of something is left multiplication of that something by a. And in fact, this example is a lot more general than it looks, because we're going to find a way to associate to every linear map a matrix. And we're going to do this by choosing bases for the domain and codomain of the linear map, and then writing the inputs and outputs of the function in terms of those bases. So here's the definition. It's quite complicated, so it involves a lot of ingredients. So I'm going to read it out and then immediately do an example so we can see what's going on. So we begin with a linear map T from a vector space V to a vector space W. Then we take a basis for V, so I'm going to call my basis for V B, and we take another basis for W, C. Now, the thing to remember about these bases, the important observation here, is that if you look at T of one of the B's, so let's say the jth element of your basis for V, well, this is something in W. It's an element of W. And if it's an element of W, you can write it in terms of the basis. You can write it as a linear combination of our basis for W. So we can express T of Bj as a linear combination of our basis for W, so of curly C it was called. So we're going to give some notation for the scalars that we use when we do this. So T of Bj can be written as a linear combination of the C's, and so we will call the scalars we use A1j, A2j, A3j up to AMJ. So the notation there is this. Then these scalars naturally form a matrix. We've got a bunch of scalars where the first coordinate, the i's, go between 1 and m, and the second coordinate, the j's, can go between 1 and n. So those things naturally fit into an m by n matrix. And we call that n by n matrix, we write it like this, and we call it the matrix of T with respect to initial basis B and final basis C. So there's a lot of stuff going on there. Let's try and find a simple example so we can work out what's going on here. So well, actually, before we do this, let's look at just what's happening in this matrix. So if we have our matrix, we know that it has m rows. We know that it has n columns, like this. And I'm going to think what happens. What does the jth column tell you? So column J. Well, column J is exactly the entries in. Column J is exactly the scalars A, I, J, as I runs from 1 to m, which tell you how to express Bj as a linear combination of the C's. So column J tells us how to express T of Bj as a linear combination of the C's. So put this way, it seems actually quite simple what's going on. All you're doing is saying I can express T of B1 as a linear combination of my basis for W, and I write the scalars into the first column. And I can express T of B2 as a linear combination of the C's, and I write the scalars that it took to do that in the second column, and so on. And that's all there is to the definition of the matrix of a linear transformation with respect to a certain initial basis and a certain final basis. So let's look now at some examples of actually doing this. We're going to take T to be the linear map from r squared to r cubed, given by T of AB is this expression here. You can check that that really is a linear map, and you should check that. So let's take some bases for our initial and for our domain and codomain, and then work out the matrix of this with respect to those bases. So we're going to take the standard bases in both cases. So let's let curly E be the standard basis of R squared. So we would write this E1 and then E2, where E1 is the vector 1, 0 and E2 is the vector 0, 1. I'm going to take E prime to be the standard basis of R cubed. So E1, E2, well, I guess I better use a slightly different notation here. So let's say E1, E2, E3 all primed, the standard basis of R cubed. So the question is, we're going to find, we want to find the matrix of T with respect to the initial basis, the standard basis of R squared, and final basis, the standard basis of R cubed. That wasn't a very good 3. That's better. Okay, so the question is, what is this? How can we work it out? Well, we know that the first column would tell us about the scalars that we needed to express T of the first basis element for the initial basis in terms of the final basis. So we need to work out what is T of E1. Okay, that's T of 1, 0, which is, what do I have? 1 plus 0, 1 minus 0, 2 times 1 plus 0. Okay, and I need to express this as a linear combination of my final basis. Well, that is 1 times E1 prime plus 1 times E2 prime plus 2 times E3 prime. Okay, we have now worked out the first column of our matrix. So let's start filling in the matrix. This matrix, the matrix of T with respect to initial basis E and final basis E prime. What size is it going to be? Pause the video and answer that question. So this will be a 3 by 2 matrix, and we've just figured out the first column. The first column is 1, 1, 2, because those were the coefficients which we've just seen we needed to express T of E1 in terms of the final basis. So to get the next column, let's do it in a different color. T of E2, that's T of 0, 1, which is 1 and then minus 1 and then 1, like this, if my arithmetic's working today. 2 times 0 plus 1, that looks right to me. Okay, again, it's easy to express this in terms of our final basis. It is E1 prime minus E2 prime plus E3 prime. So we've just figured out the second column of our matrix, and that second column is 1 minus 1, 1. Okay, we've done it. That is the matrix of this linear map T with respect to initial basis, the standard basis of R squared, and final basis, the standard basis of R cubed. Okay, let's do another. So we will take an example where we have the differentiation map. The differentiation map D from the vector space of all polynomials of degree at most 3 in the single variable x to the same vector space, and D is the differentiation map. So let's take as our basis, we're going to take both bases, so initial and final bases. So let's call this curly B is going to be 1x, x squared, and x cubed. So the question is, can we find the matrix of D with respect to initial basis B and final basis B? So in this context where you're looking at a linear map from a vector space to itself, and when you just choose to use one basis, so the same basis as both initial and final basis, we sometimes call this just the matrix of D with respect to B. So if we're using the same initial and final bases, we'll just say the matrix with respect to that basis. So let's work it out. What we have to do is just apply the linear map D to each of our basis elements and look at the coefficients we need to express the image of our basis element as a linear combination of the basis elements. So let's write down the answer or write down the grid and then fill it in. We have a 4-dimensional vector space, and we're going from a 4-dimensional vector space to a 4-dimensional vector space. So this will be a 4x4 matrix like this. And the first column is going to come from working out d of the first basis element, so d of 1. That's d by dx of 1, which is of course 0. Okay, so that's 0 times 1 plus 0 times x plus 0 times x squared plus 0 times x cubed. So my first column will be 0, 0, 0, 0. Okay, next let's do the second basis element, d of x. So this is 1. So that's 1 times 1 plus 0 times x plus 0 times x cubed plus 0 times x cubed. So that's 1 plus 0x plus 0x squared plus 0x cubed. So my second column is going to be 1, 0, 0, 0. So if you like, you can think of the rows of being labelled by the initial basis, by the final basis rather, and the columns by the initial basis. Okay, next one, d of the third basis element, d of x squared is 2x, so that is 0 times 1 plus 2 times x plus 0 times x squared plus 0 times x cubed. I can see I've not quite got my labels right there, have I? That should have been x squared and x cubed. Okay, final one then, final entry, d of x cubed is 3x squared, which is 0 times 1 plus 0 times x plus 3 times x squared plus 0 times x cubed. So there is our matrix of D with respect to initial and final basis B. Okay, let's make a couple of observations then before we stop the video, which is, first of all, if you look at the matrix of the identity map with respect to the same initial and final bases, it's always going to be the identity matrix. So the reason for that is that if you're working out the jth column of this matrix, the matrix of the identity with respect to initial and final basis B, so if we have B is B1 up to Bn, let's say, then the jth column of the matrix of the identity is determined by, well, what do I have to do? I've got to take the identity, apply it to the jth basis element, and express the result in terms of my final basis. And of course the final basis being the same as the initial basis, this is, well, it's bj again, so that's just 0 times b1 plus, and so on, plus 1 times bj plus, and then 0 times everything else. So that column, the jth column, is this, right? It's got a 1 in position j, and it's got zeros everywhere else. That is the jth column of the identity matrix. Alright, so if you take the matrix of the identity with respect to the same initial and final bases, then you'll just get the identity matrix. But on the other hand, if you take the matrix of the identity with respect to different bases, if they really are different, then this will never be the identity matrix. So as a simple example, let's take the matrix of the identity on R squared with respect to two different bases. So let's say we take, I'm going to have as my final basis, so B is going to be the basis 1 minus 1, and then 1, 1, and C is going to be the standard basis for R squared, so 1, 0, 0, 1, and what would be the matrix of the identity with respect to initial basis B and final basis C? Well, the identity of 1 minus 1, the first element in our initial basis, is, how do I express that in terms of the standard basis? Well, it's 1 times 1, 0 plus minus 1 times 0, 1. So the matrix of the identity would look like, we just worked out the first column, we found it's 1 minus 1. Okay, it's actually the same as the first basis vector in B. And then if we do the same thing for the second basis vector from B, from our initial basis, we get 1 times 1, 0 plus 1 times 0, 1. So the second column will be 1, 1. So actually you can see what's going on here. We're just putting the column vectors in B into a matrix like this. And you can see this is not the 2 by 2 identity.